Why is an ideal solution important for entropy of mixing? Imagine mixing two liquids and seeing them blend smoothly without any fuss. Now, think about how this simple process relates to the idea of entropy, or disorder, in a system. When two substances combine, their molecules spread out and become more randomly arranged. This increase in randomness is what we call the entropy of mixing. But understanding this process gets tricky when molecules interact differently, which is often the case in real solutions. That's where the idea of an ideal solution comes into play. An ideal solution is a simplified model where the molecules of each component behave independently, and there are no extra energy changes during mixing. This makes it easier to predict how the entropy will change because we don't have to worry about complicated interactions. In an ideal solution, the molecules don't stick together or repel each other differently than they do with themselves. This means the heat content, or enthalpy, stays the same when the substances mix. Because there's no heat absorbed or released, the change in entropy depends only on how the molecules distribute themselves. The formula for the entropy of mixing in an ideal solution involves the mole fractions of each component and the natural logarithm of those fractions. Mole fractions are just the parts of each substance in the total mixture. The formula shows that the entropy always increases when mixing occurs, because the logarithm of a number less than 1 is negative, and the negative sign makes the whole thing positive. This positive change reflects the fact that mixing makes the system more disordered. The reason this is so important is that it allows scientists and engineers to predict whether a mixture will happen spontaneously. If the entropy increases enough, the process is likely to occur naturally without needing extra energy. In real solutions, molecules do interact differently, which can change both the enthalpy and entropy. But the ideal solution acts as a baseline or reference point, helping us understand the pure effect of entropy during mixing. Knowing this helps in designing chemical processes, creating new materials, and understanding how gases mix quickly and spontaneously under constant temperature and pressure. So, in simple terms, an ideal solution is key because it lets us see how mixing increases disorder without the complication of energy changes from molecular interactions. This makes the principles of thermodynamics easier to grasp and apply in real-world situations.